This media was gratuitously produced by Clear Contributions Audio and Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
Any questions? Anything you run into that you weren't sure about? Yes, ma'am.
Okay, so when you're like filling out whether the molecule is like primary, secondary, if it's like not the carbon, if it's the amine or the alcohol, and if it's connected to more than one carbon, is it the carbon that has the highest number?
Good question. So with the amines, they can form up to 4 bonds with carbons, and so in that case, for an amine, you count how many carbons are directly attached to it, not what kind of carbon it is.
Okay, so it's still the number, right? Because most of the other ones, right? So if it was like
The
a secondary
alcohols,
alcohol where it was only attached to 1 carbon, it's whatever. Like if the carbon attached to 2 carbons and the alcohol is a 2.
Yeah.
But if it's an amine, it's however many carbons it's attached. If it's attached to multiple carbons, it's a number.
Exactly.
Is that for everything, right? So if it's attached to more than 1 carbon, it's the number of carbons.
Yes.
Okay.
Good.
Yep.
We have another question here. So, a lot of the times, whatever is hooked onto the carbon, you name it whatever the carbon is, right? And other times, it seems like it gets its own label. Like nitrogen was the example that we found, right? It had 3 bonds, so it'd be tertiary. What's the difference? How do you know when to just label whatever the carbon is, or when to label it as itself?
It's what the atom tends to like to, the number of bonds that the atom tends to like to form determines that. So carbon and nitrogen are the only ones over here that are going to tend to form a lot of different bonds. We haven't done anything with ethers. Oxygen could form 2 bonds, but we haven't done anything with ethers in describing whether they're primary, secondary, or tertiary, because an ether by definition has to have 2 carbons attached to it. So that one is kind of like, there's no point to describing it because an ether is an ether. Whereas an amine, you could have 1, 2, 3, or 4 carbons attached to it. So that's why it becomes important how many. Alcohols, the O where it has an H attached to it, can only form 1 attachment to a carbon. And so same thing with the halogen, same thing with hydrogen, since they can only, no, not only, since they usually only are going to form 1 attachment to carbon, that's when you describe the kind of carbon it's attached to. So carbon or nitrogen, count how many carbons are directly attached. Everything else, look at what kind of carbon it's attached to. And that's just a hard and fast rule. Anything else? I have to try and figure out the technology today. I can't just skate around it today. All right then, today we're launching in, yes?
Sorry,
Oh gosh, no, go ahead.
So vanillic, is that any double bonded carbon or only attached to another carbon?
Vanilla has to be a double bonded carbon.
Attached to only carbon. Or any double bonded carbon?
Any double bonded carbon.
Okay.
Yep. Good. Okay, I wanted to explain this. This was my husband's idea. I'm trying it out. This, the print on it is a little small, so I could fit everything in. So I gotta see if I should redesign this or not. I put every single rule for the whole semester on here. Yeah, so this is it, the whole semester in 2 pages. So tell me how it works for you and what I can do to redesign it or whatever. But this was my husband's idea because he said, I always like a roadmap to know what we're doing and to have something to refer to. And I thought, well, this is a great idea too, because then instead of me saying, today we're talking about this little piece and tomorrow we're talking about this one, you can't see how it all goes together. So this tells you how everything's interconnected, how it all fits together and everything. So I was going to explain to you what we're doing here on this first page with the red boxes. This is the first 4 chapters, the first 2 tests. With every rule on here, and all I got to do is show you how to apply these rules and make you feel confident in how to apply them and know what you're doing first. So anyway, on the left-hand side with the red box here, rules 1 through 4, that's chapter 1. We're going to be working just on rule number 1 today and how to do that. But this is the whole first chapter. Coming down to the bottom of that same box is chapter 2, and then that entire box right there is the first test. The box on the lower, the 2 boxes on the lower right are chapter 3, and the box up here is chapter 4. That makes the whole second test right there. Okay, so that's where we're going. I've worked this out when I was thinking about how do I name a molecule, what are the steps I need to take, and what order do you need to do everything in. This is what I came up with. So it's very methodical, and if I can get you to just go down this like a checklist, first I do this, then I do this, then I do this, and you just do these 5 steps, it's always going to work. This is a lot like math class. That's one of the reasons why I love organic chemistry. If you learn a principle, then you can apply it to everything. So I was explaining to the other section the other day, most of the time the way organic chemistry is taught is where the professor says, if you add 11 and 12 together, it's 23. Write that down, remember that. If you add 15 and 16 together, that's 31. Write it down. And so you memorize the sums of different numbers, that you recognize, and you don't even know how to add all of the stuff in between, really. You just learn specific things that you're numbering. And sometimes, to be fair, they might throw in a few reasons why things happen the way they do, but it's kind of lost in the idea of you're focusing on specific reactions or whatever. In here, I want to teach you that 1 plus 2 is 3. 1, 2, 3. And now when you add the column, you add columns together, and so 1 plus 2 in this column is 3, and you write it down. You can add anything together. Okay, so these steps are what I've come up with for how you actually name a molecule. And just apply it. It will always work. So the first chapter, this left column is IUPAC, International Union of Pure and Applied Chemistry. These are a set of rules, and it's a very methodical way of naming compounds. So the deal is that, I'm sorry to keep backtracking, I'm bouncing around this morning. This part down here is called Common Name System. And the common name is a lot older, and it's to an extent where somebody looked at something and said, I think I'm going to call that molecule Bob. And then everybody else is calling that molecule Bob. And so at some point, it just started breaking down because you can't come up with a very systematic way of naming molecules that way. And now there's well over 64 million different organic compounds that are known. So, at some point somebody said, we got to come up with something that's going to work a little better. So that is the whole basis for this first naming nomenclature system we're going to be going through. Is somebody came up with something that was very systematic. And that's why it's also known as the systematic method for naming molecules. I'm not doing that anymore. Okay. So it's very methodical. There are, of course, a lot more rules than what I'm showing you here. But we're going to just learn the basics of how to name a molecule. But you're going to find that once you get these basics down, you can name quite a lot of molecules. I'll also show you later, as long as I'm not going to blow you away, that you can look on a sheet for a pharmaceutical or something and see a systematic name. And it goes for like lines and lines and lines and lines. So we're not going to do that, but oh, look at this. Oh, look at, yay. Woo! By the way, Dr. Johnson is in the room right above me, and he somehow knew it was me. The other day when I was messing around with this person, I kept trying to get onto his network, and he was trying to like, no, go away. So he called me out. Okay, at the beginning of each chapter and each workbook chapter, you're going to see that I have the whole chapter boiled down into like half a page, so that when you're reviewing for a test or something, you can refresh your memory on the basics of the chapter. I've only given you the workbook chapter because, as I said, it's very expensive to print the color copies. So for right now, we're going to just work with the workbook until the actual textbook comes in, and you'll use this as a lecture note system only, not also to take notes as you're reading. Yes, ma'am?
Do you know when the books will be in?
I don't. I'm afraid I don't.
Okay.
I'm sorry. If it gets to be too long, I'll just launch off and print those also. But the textbook that goes with this is 70 pages of color printing. So I thought, well, we'll see once what we can do with this first. Okay, so this chapter just tackles the first 4 steps, because the 5th step with stereochemistry is very complex and it takes a lot to explain it to you, so I've kind of broken it down. So for this chapter, you don't have to worry about that step. The first 4 steps are, you have to identify the following characteristics in the molecule in the same order that I'm presenting them, and I'll show you why that is in a minute. But first you highlight functional groups, then the parent hydrocarbon, and then the substituents that are attached to it. So the functional groups I told you to memorize and make flashcards. We're going to be adding to that list later in the year, but for right now you're just looking for an alcohol group, an amine, a double bond, or a triple bond. Any of those are functional groups. Any other atom that you see in the molecule, it doesn't matter what it is right now. I'm only going to be feeding you stuff that has other things. But those are substituents. So that includes halogens, fluorine, chlorine, bromine, iodine. I don't know why the halogens are treated differently. It seems unfair. Why are they excluded from this very important list? I don't know. Somebody has something against halogens. But anyway, they're substituents. Alkyl groups. Yes.
I'm not sure. Isn't this first one supposed to be an alcohol group at the top?
Very good question. So an alkyl group, you're going to see that it's any carbons with single bonds, so like alkanes, but when they are included in the name of the molecule and they're not part of the parent hydrocarbon, you change the ending to YL. So a methane becomes a methyl group. And so that's why an alkane becomes an alkyl group. So you're gonna have to try and work with my Michigan accent. I'm gonna try and make it real clear and everything, but alcohol and alkyl and alkane and alkene, and it kind of gets to be a little bit similar sounding. I'll try and emphasize it though. So this is any carbon groups that aren't included in the parent hydrocarbon, halogens, and an alkoxy group is an alkane with oxygen. In other words, it's part of an ether. Okay, but we'll go over the substituents a little more carefully later. This is just kind of a preview of where we're going. This is why I want you to have different color highlighters, so that you can highlight these different components. It'll make it a whole lot easier for you to see what you're doing. So throughout the book, what I've done is I've got the functional groups in red or pink that you have, parent hydrocarbons in blue, and substituents in green. Then you write the name for each thing. The substituents go first, then the parent hydrocarbon, then the functional group. So it goes in the opposite order of how you found them. If you have an alkyl group, carbon group, it has a YL ending change. If you have an alkoxy group, then it has an oxy group, or oxy ending. And if you have a halogen, it has an O ending. So fluorine becomes fluoro, chlorine becomes chloro, and so on. The functional groups have specific endings also, and part of your homework tonight is going to be to learn these different endings for the different kinds of substituents and functional groups. But alcohols are all, amines are amine, alkenes are ene, and alkynes are ine. Okay, so you write that in. If you have more than one of a specific group, like you have 2 bromines in there, then you put the prefix di in. But do that after you've done everything else, otherwise you're going to get messed up on the alphabetization. Is that a word? I don't know. And then you have to say where everything's attached. So I'm going to teach you how to number the carbon chain. That's everything. So we will launch into this. You're going to get the hang of this pretty soon, but I'll tell you why I got the color coding the way I do. Red is a warning because the functional groups are very, very, very important to a lot of the other things that you do. That's why you locating them first. So that's why it's in red, like, whoa, don't ignore me. The base of the name for the molecule is the parent hydrocarbon, so base in blue. That kind of went for me. And once you highlight something in green, you're ready to go to the next step. So substituents are in green. All right. So I've already explained learning objective 1 that you have alcohol, amine, alkene, alkyne are functional groups. Anything else that's not highlighted in blue is going to be a substituent. That includes carbon groups, halogens, and so on. Okay. Now for figuring out the parent hydrocarbon. That's going to be a tricky one. This is what we're going to spend the rest of our time on, is the parent hydrocarbon. I'm on page 3. Do you see where I am?
No.
I'm so sorry. Workbook. Oh, look at that. That's why you were flipping around. I was wondering, what are they looking for? Almost there, almost there. There! Does that match up with what you have? All right, fine. All right, so often I'm going to be giving you reading assignments, or this is a place for you to take notes. So the 3 groups that are substituents are halogens, good, alpha groups, and alkoxy, which are oxygen with carbon if you are naming an ether.
Say those one more time.
Sure, halogens, alkyl groups, which are just carbon groups, single bonds, and alkoxy, which is carbon plus oxygen. That's you would be doing for an ether. And the functional groups. Alcohol, amine, alkene, and alkyne. Yeah, so you have the double bond, the triple bond.
Sorry, which one's the double and which one's triple?
I think it's double alkyne.
Alkene is double and alkyne is triple. So it's kind of alphabetical in order of the increasing number of bonds. Alkane, alkene, alkyne. Like I said, now we're going to conjugate verbs. Okay, now you have to name everything off of a base structure. The base structure is what's called the parent hydrocarbon. As it sounds, it's a hydrogen-carbon containing group. Just hydrogen and carbon, that's all. And what you want to do is find the longest continuous chain of carbons connected together to each other without being interrupted or anything. So this is like, you know, when you go to Pizza Hut or something and you get the kids' placemat and you can do the little games on it, and so you find yourself doing that. This is kind of like one of the kids' games. We got to start on one end with a carbon, and now you got to trace through and find the longest continuous stretch of carbons. So that is one of the key rules for identifying the parent hydrocarbon. But I'm going to have you put that on second. Because it isn't just
Would so I have a question. You said the longest identify the longest chain of carbons uninterrupted.
So you don't want to trace through a nitrogen, for
Oh,
instance,
okay.
or
I thought you were
an
talking about like
oxygen
if
or
it would
something.
like
So it's
to
gotta be-
bend down. So like
Right. No, we're
Oh,
going to talk
okay.
about you can bend it. But the important additional, don't forget this, I'm having you put as number 1. You have to include any carbon that's directly attached to a functional group. That's why you're highlighting any functional groups in red, so you don't miss that idea that you have to include the carbon directly attached to it. So therefore, it might not be the very longest continuous tracing of carbons. It has to be the longest continuous tracing that includes a carbon directly attached to a functional group.
So for number 2, it's not just the longest stretch of carbon, but it's the longest stretch of carbon that's attached to a functional group.
So it has to include the functional group. All right, so now I've got to get you to think in 3 dimensions. Unfortunately, when you have things presented to you in 2 dimensions a lot, I'd like to make a book that has a holographic image that pops out of the book at you. But yeah, for right now, you got your molecular model kit. But usually, when you see a molecule written, and it's written like this, and you start getting this notion that it's very flat like this. But as I explained the other day, it actually is kind of zigzaggy like this because you have tetrahedral geometry on all of the carbons, and so it looks like this. But notice that you also can have bond rotation because these are single bonds, and so therefore, see, up and down and to the side means nothing because you do have bond rotation. And so when you're looking for the longest continuous carbon chain, you're not just going 1, 2, 3, 4, oh, look at that. There's 4. You gotta also consider anything coming up or down in addition to off to the side. And so in this example here, I'm gonna have to bring this down a little bit because I'm short. My family will tell you all about that. Anyway, the longest continuous carbon chain isn't just this part right here. You also have to look up and down. So anytime you come to a carbon where you got carbons coming off in different directions, you have to look in every direction and see, oh, if I go this way, it's only 1 more carbon, but if I go this way, it's 2 more. So you have to look up, down, sideways, everything when you're tracing. So this one, you would go 1, 2, 3, 4, 5, 6, 7, 8, 9. See how to do that? So if you were going to practice with the highlighting, you'd highlight the OH group here in red, and then it'd be like, I've got to include that carbon, and then you would trace through, and the rest of these carbons in this longest continuous would be your parent hydrocarbon, and they would be in blue. See how if you put it in different colors, you can actually picture what's going on instead of just trying to visualize. All right, now do you also notice, well, I'll give you a minute. So the parent hydrocarbon is in blue. That's the 9-carbon sequence that I traced out for you here. You also notice, though, that the parent hydrocarbon didn't catch 2 of the CH3 groups. Those are substituents, and so those would go in green. Okay, so that is how you would do step 1. And we're just going to keep working with that today. I'm going to show you some variations on that and everything. But that's locating the functional group, the parent hydrocarbon, and then the substituents. Okay, so now as far as filling in the notes, the important point that's illustrated by the, by the example that you just worked, what's the thing you got to keep in mind when you're working a test question or something like that? What am I trying to show you here? Don't forget you can turn corners. Look in every direction. And the reason why you can do that? What do you think? How do you want to say it? Why can you turn corners? Why don't you just go left to right?
Because the paper representation isn't a very good representation of reality.
Yeah, sure. You got tetrahedral bonds here, and you got bond rotation, so things can twist around. Up, down, and sideways are all equivalent. All right, I want you, without coaching here maybe, to highlight the next example here, how you think, and then we'll talk about what you got going on and see if you got questions. That's why you got a pen or whatever, you can always redraw it, huh?
You want to see fiber?
That's right. It has to contain a carbon directly attached to the functional group, and that's why you're locating the functional group first. Why what? Because it has to include the carbon directly attached to the functional group. Otherwise, you're going to find out that you're going to run into problems with naming it, because you're going to be able to name a CH2OH group. Great. So, yes, ma'am.
It doesn't have to start with the functional group next.
Good. Yes, it does not have to start with where the functional group attaches. It only has to include a carbon that is attached directly to a functional group. Good. So the rules are written very specifically the way that they're applied, and so I just got to get you to see all the different issues and be able to apply them consistently. How many carbons did you come up with for the parent hydrocarbon in this example? 5. Very good. So your first step is you highlight the OH, then it has to include any carbon directly attached to the OH. It doesn't necessarily have to be the first carbon of the sequence, but in this case it is. It's just a coincidence. So you're starting from here. When you come to this carbon, you have to make a choice. Do I want to go this way or this way? This way gives you more carbon. So your parent hydrocarbon comes this way. This is your substituent.
I agree.
Mm-hmm.
And then the right of it is the parent.
The what?
The right of it is the parent.
To the right is your substituent, so it's in green.
So then where's the parent?
The parent hydrocarbon is this one. That's the longest continuous grouping of carbons. All right, and so what's an important point that's illustrated by that?
And it's not necessarily the longest carbon chain, it's the longest one that's attached to a functional group.
Right, so I'm trying to psych you out here, and because you could have included more carbons if you went straight across, but you can't do that. It has to include the carbon that's directly attached to the functional group, even if that's not the longest possible carbon tracing that you could have. That's why I'm getting you to highlight the functional group in red as your first step, because that's important to determining the parent hydrocarbon in the next step. Okay, I just want to do one more thing here, but before we go on, I just wanted to show you something that I've got here, and I don't know if it's going to be helpful to you or not, but you notice that I have questions off to the side here. The idea is at the end of the day or before a test or whatever, you can fold your paper over so that it just matches up to this line here, and you can go down there and you can quiz yourself and like, do I understand this concept? And if you don't know something, you can open it up and there's the answer right there so that you can kind of, do like a self-quiz. Okay, so your assignment for tonight, we're going to keep going with tracing the parent hydrocarbon a little bit more tomorrow. Oh, that reminds me. The class meets 4 days a week in addition to the lab, so that I can give you extra time to kind of learn the stuff, and it's not like a fire hose and everything. So if it's a class day, you're seeing me. So tomorrow we do have class. Tomorrow morning at 8 o'clock. Okay, at the beginning of the semester, I always have students who miss Thursday because they weren't really sure what was going on.
Can we see you Friday also then?
Don't say it like that. You mean I gotta see you on Friday too?
Well, I was just
I heard you. There's no backtracking from this.
I was just wondering.
Yeah. All right, what I want you to do in preparation for what we've got coming up next. Do I have it? It might be in the textbook. No. All right, then I'm going to write it on the board here because I can't find it right off. Here are the names for the parent hydrocarbons. I'd like you to learn the first 5 for starters. The next 5 are way easier. This will be the ones that take the most amount of work. One carbon is methane. 2 carbons is ethane. Why did they do this? Everything sounds so similar in organic chemistry, huh? 3 is propane. That's right, like your barbecue grill tank. 4 carbons is butane. And once we come up to 5 carbons, that's where it gets easier because now it's like based on the stuff that you've learned in geometry class. 5-sided things are pentagons or whatever. This is a pentane. Do you notice something common to all of these words? Ane, because they're alkanes. So if you can start flashcarding these, we're not going to quite be there yet. I mean, we might get there by tomorrow, but this will kind of give you a basis that we can start working with how to name the compound in step 2 for a little bit later. Okay? All right. Go team!